In the previous video, we started looking at an example of a initial value problem for a first order DE, and we said that if we use solution methods that we learned earlier in the course, we said the solution of that initial value problem is 10 e to the t minus 6. In the previous video, we had just gotten started on solving that problem using Laplace transforms. Step 1 was to take the Laplace transform on both sides of the differential equation. Then we used the linearity property, which gave us this on the left-hand side, and the Laplace transform of 6 is 6 over s. So now we're going to pick up the solution of this differential equation using Laplace transforms from here. In the next step, we're going to use capital Y of s to denote the Laplace transform of little y using the usual notation. Small letters in the time domain, big letters in the Laplace transform domain. And we use the operational property here to replace the Laplace transform of y prime with s times the Laplace transform of y minus y of 0. In the next step, we just plugged in the initial condition which was given, and now we're going to solve that for big Y. So we collect terms involving big Y on the left side. That's what's happening here. And the terms that don't involve big Y are 6 over s and 4 on the right hand side. Looking ahead a little bit to the next step, I went ahead and I found a common denominator. On the right hand side is 6 plus 4s over s, and then I divided through by s minus 1 to get this expression for big Y of s, the Laplace transform of the solution that we're looking for. Notice with the Laplace transform approach, the initial condition has already been incorporated automatically, which is different from anything we've ever seen before earlier in the course. The other thing to pay attention to here, which I always recommend students to pause when they're doing this kind of thing and check, you should always end up with the characteristic equation on the left-hand side at that step right before you're done solving for y. So if you used lambda, your characteristic equation for the left-hand side of that differential equation that we started off with would be lambda minus 1, and that's basically what we're seeing as the coefficient of big Y, and you should always stop and check that. If you don't see your characteristic polynomial showing up at that step, then you know you probably did something wrong earlier in your solution. So in any case, now we're going to work with this expression for big Y, and we're going to be using partial fractions a lot in connection with Laplace transforms. A lot of our work from now on is going to involve partial fractions, so that expression for big Y, this is a relatively simple example of partial fractions. We'll certainly see more complicated examples later in the chapter. The student may or may not find it helpful to review the technique of partial fractions. We touched on it a little bit way back in chapter 1, but that's something we are going to be dealing with a lot here. So we're looking for a solution, an expression for big Y of the form a over s plus b over s minus 1. The theory of partial fractions, when we have two distinct linear factors, tells us that it's always possible to do that. So now we need to determine a and b, which is what's happening next here. So we clear all the denominators, and so that previous equation is equivalent to 6 plus 4s equals a times s minus 1 plus bs. The simplest way of dealing with this right now, when you just have linear factors and nothing's repeated, is to just plug in values of s that make it quick and easy to determine the coefficients a and b. So if we plug in s equals 0 into the previous line, we get 6 on the left hand side. The b term drops out when s is 0, and we just get the equation 6 equals negative a immediately. So we know the value of a must be negative 6. Similarly, if we plug in s equals 1, we'll get 10 on the left hand side. The a term drops out, and we just get b on the right hand side. So that determines the value of b. b must be 10. So taking those values for a and b, which we just found, and plugging those back in here, we get this expression for big Y. And now that's easy to invert. When we say invert here, we mean we're taking a function of s, a function in the Laplace transform domain, and going back to the time domain. We're finding the function of t that has that function for its transform. And based on our earlier work, including the idea of linearity, hopefully it's clear that that function of t is the function that we're looking for. So the point of the method of partial fractions, this work here, the method of partial fractions, the point of that work was to get our function big Y of s in a form that would be easier to invert. So once we had it in this form, it was easier to basically read our table of Laplace transforms going backwards, including the linearity property, and say that must be our solution of that initial value problem, which agrees with the solution that we found earlier using one of the earlier methods covered in the course. Now at this stage, I'm not claiming that the Laplace transform method is easier. In fact, if you've never done anything like this before, it probably seems like a more complicated way of doing it. So I'm not making any claims that this is necessarily easier. We're going to have to talk about that later in this chapter when we have more experience with Laplace transforms, talk about the pros and cons of Laplace transforms. We'll have that discussion later on, but for now I'm just trying to show you that at least it is possible to solve differential equations using Laplace transforms. I always like to try to do at least one example as soon as we know enough about Laplace transforms to be able to do that. Here's an example where we use the definition of Laplace transforms to calculate the Laplace transform of that function. At this stage, that's the only way to do this. So because the function is defined in pieces, we break up our integral into pieces over each of those intervals, or our function is defined as whatever constant value it has on each of those intervals. On the first interval, we pull out 2, the constant value of our function. On the second interval, we pull out 1, the constant value of our function. And the third interval, our function that we're integrating is 0, so the integral of 0 is 0. Then we just anti-differentiate and use the fundamental theorem in each of those two terms. I use the minus sign here to flip the limits of integration. Pretty much what I've been doing in our earlier calculations. And then I plugged in the limits of integration. Everything contains 1 over s as a common factor. So I pulled that out. Sorry, I just covered up the 1 over s common factor, which I pulled out. And then I just plugged in t equals 0, t equals 3 there, t equals 3 there, t equals 5 there. And combining the two middle terms, that's our expression for the Laplace transform of that function. In exercises 23 and 24 in my book, I asked the student to try using the operational property to prove some of the Laplace transform facts, and hopefully it will be helpful to go through 1 or 2 examples here. In exercise 23a, if we take f of t as e to the at, and differentiate that, and check the initial value, then we take our operational property here and plug everything in. So here I plugged in the derivative, and I plugged in my function. And on the left hand side I can pull out the a, and then I just have the Laplace transform of my function. The right hand side I have s times the Laplace transform of my function. And then I just solve that for big F. 1 is s minus a times big F. So big F is 1 over s minus a. That's kind of a tricky way, but it does show the power of using the operational properties as another way of proving one of our basic Laplace transform facts. Exercise 24a is similar. If I want the Laplace transform of sine bt, I found the first and second derivative, and then I use the operational property for the second derivative, which was given in the problem, and plugged everything in there. Plug in the second derivative, and if f of t is sine bt, f of 0 is 0, so the middle term drops out. Cosine of 0 is 1, so you just end up getting minus b there. So simplifying that using linearity, on the left hand side, minus b squared times Laplace transform of f is s squared times Laplace transform of f minus b. And we just solve that for big F here, and we got the standard formula, which is in my table of Laplace transforms for the Laplace transform of sine of bt. So those derivations in exercises 23 and exercise 24 are a little bit tricky, perhaps, but the advantage of proving those things in that way is we can use the operational property now that we know the operational property and avoid having to do some complicated integrals.